so I recorded it. I start recording. Okay, so that's it for the logistic part. And when it comes to, if you ask me for an extension, okay, so I already give you so many times to do to do your assignments and labs. Now, if the deadline is passed, the adaptive policy will be enforced. So you are the king. You are the man who will decide whether you need an extension or not. As you can see, I did not upload any solution yet. So I'm opening the floor for you to to submit your assignments. Okay. That's it for the for the logistics part of the course. And don't be scared. I know, it's something psychological, okay, you said that it's an online course. I will not study. I will study on the spot. But listen, that doesn't apply here, okay? So what you need to do is at least you need to watch the videos, okay? And you will be fine, okay, guys? So if you have any question, do you have any question? Okay, yeah, I want to ask you something. Okay, so I'm thinking of, combining assignment 5 and 6 in one assignment. And instead of giving you so many exercises, I'm going to give you exercises that will cover module 5 and 6. You like that? Or should I, after this lecture, I'm going to post assignment 5. It's going to be just for module 5. And then next week, I'm going to post assignment 6. Or do you want me to upload one single document for everything? And it's going to be the deadline till the end of the course. Combine it. Okay, Louisa decided. Combine it. Okay? Okay, guys. So yeah, let's question. Okay. Yeah. So don't expect me to give you just one question per module. No, I'm gonna give you something that will cover the whole, the last 2 chapters in your textbook, which are the module 5 and module 6, and at the same time you will have a penalty of time to do it, but don't be comfortable. Okay, so don't get comfortable, otherwise you will not be able to do anything. Okay, guys. So that is for the logistic part. Do you have any questions regarding the regarding the laws or? And yeah, when it comes to the grouping, I know that some of the students, they drop the course. Okay, so you work alone by your group, or you can share the work with another group, but we will not move you. Okay, you remember, I have already told you, it's a Catholic marriage. Okay, I'm not changing my religion now. Okay. So that's it for the logistics. Let's continue about the synchronous sequential circuit. I'm gonna disable my camera because I don't want to see my face. Okay, but I just open it just to, to give you the feeling that we're still alive after this COVID thing. Okay, so guys, when it comes to, okay, well, stop it, man. Okay, yeah. So guys, when it comes to to sequential logic, okay, so the difference between combinational logic that we have studied so far in the course and the sequential logic is that in combinational logic, the output of the function will be will be depending on the input only. That's it. So if you have multiple inputs, in the case of the full adder, if you remember, so if you have A, B, and carry in, you will have sum and carry out. There is nothing loop back from the output to the input. Okay, so that will create, yes, a logical circuit, but this logical circuit will be time independent. What does that mean? That based on the value of the input that I have, my output will change. Okay, now the problem when it comes to the combinational logic, there is no such a memory. Suppose that you are doing some calculation and you're adding A plus B, and then you want to add it to the C. So unless you memorize what was the addition, between A plus B, you will not be able to do it plus C, okay? So what we like, the goal from sequential logic is to create some kind of memory elements. Those memory will store the results, okay? So suppose that you designed a, like similar to lab 4, you designed that 8-bit full adder, and at the end, if you move the sum somewhere to the to something called flip-flop, okay, so you will be able to preserve the values of your operation forever, okay? So the basic building block when it comes to combinational circuit is the logic gates that we have covered. When it comes to sequential logic, the basic building block is the flip-flop. If that flip-flop has no clock, it's called latch, okay? And the latch will capable to store 1 bit and its complement, okay? So that is briefly what do I mean by sequential logic. And sequential logic, there will be time dependent based on, you know, the clock value. When it comes to the synchronous one, the value of the output might change, okay? Okay, so let's revisit all the types of flip-flop that we have covered on the previous lectures. So the basic type is the SR flip-flop, okay? And as you can see, you have here, okay, something called truth table, something called excitation table, and I have here the state diagram and the characteristic equation. So what do I mean by the truth table? The truth table, if you remember, it will describe the main working the working feature of any combinational logic circuit, okay? When it comes to sequential logic, that truth table will be described as a functional table or characteristic table, okay? Now, the state table or the state diagram will describe what? Will describe the operation of your sequential gate here, okay? Sequential logic circuit. So we have the SR, and remember, at the SR, based on the input of S and R, the value of the output, which is because I have nothing except Q, which will be the state as well, will change. So if S was active and R was not activated, that means I'm setting my SR latch. Therefore, look at this. Therefore, if S is like equal to 1, I'm moving from state 0 to state 1. Can you see that? Can you see my my cursor? Just yes or no? Why? No, no, no. Okay. Can you see my cursor now? Perfect. So, guys, you see that the S here, the S, if it's equal to 1, so the value of the circuit here was equal to 0, okay? And if S becomes 1, if S becomes 1, what will happen? What will happen that this circuit will be setted or will be activated. So the output will become 1. You see? So if S equal to 1, the output will become 1. Okay? Now let's suppose that the output was equal to 1 and we have a set equal to 1, or we have SR equals 0, 0. So the next state or the next output will equal to the present output. So the output was equal to 1, and I have set activated as So what will happen is I'm gonna loop back to that state because the next state will equal to 1. Or if I have 0, 0, that means no change. Okay. So the no change means I'm gonna stay at 1. Now let's suppose that the reset was activated. Okay. Now if the reset was activated and I was at state equal to 1, I'm gonna reset the circuit. So what I'm gonna do is I'm gonna go back to Q0. Okay? So if my present state was equal to 1, the next state will equal to 0. Okay? So as you can see, those rows represent the transition in this truth table, in this characteristic table. Okay? And if you remember, like at the case of S and R, at which we have an active high SR flip-flop, okay, what should happen is, we're going to get an invalid output, because what will happen is both Q and Q prime will be equal to 0 and 0, and this is not what we want, because we want to cover like the high level as well as the low level. We're going to cover 0 and 1. We have to cover both combination per each bit. Okay, so that is when it comes to the SR latch. If we add the clock here, so we need, based on, this is like a positive edge triggering. So whenever that square pulse is going from 0 to 1, we will change the value as long as they are going with what? With the characteristic table of your flip-flop. Okay, so, and if you notice that we could, I derived the equation of the SR flip-flop and SR latch, and it will be S plus R prime Q. Okay, so to mitigate the overcome of having like an invalid state, a JK flip-flop was proposed. Okay, so at the JK flip-flop, the JK flip-flop follows the same operation of the SR flip-flop. However, when S and R, which is here J and K, will equal to 1 and 1, what will happen? I'm not gonna get a valid, like an invalid output. No, my next state will be basically a complement of the present state. So let's take a look on this example. So let's suppose that I am at 0, okay, and what happened is I have 1 1. In the case of 1 1 here, I don't have it, okay, so because it's gonna give me invalid. So in the case of 1 1 here, what will happen is I'm gonna toggle this present state, and it was equal to 0, it will become 1. Okay, and in case J was equal to 1, okay, what will happen is I'm gonna set my flip-flop so the output will become 1. In case K was equal to 1 and J was equal to 0, okay, so what will happen? If I was at 0, I'm gonna stay at 0. If I was at 1, what will happen is I'm gonna go back to 0, because the reset button was activated, so that's why I'm gonna go to 0. And in case of 1 1 as well, I'm gonna toggle that state, I'm gonna go back to 0. Okay, so that is basically, and the the characteristic equation, which is the Boolean function, the Boolean algebraic function of the next state, which is equal to my output here, will be equal to K prime Q plus J Q prime. Okay, now you see at the last column there is something called the excitation table. What do I mean by the excitation table? So the excitation table gives the value of the flip-flop inputs for a given state transition. So if you noticed here at the excitation, we were we're doing something called reverse engineering. So if we have a present state equal to 0 and the next state equal to 0, what does that mean? What should be the value of the input, for that flip-flop in the case of the SR to get these values? So set for sure has to be equal to 0. Yes, because if the set was equal to 1, the next state has to be equal to 1 in the case of the SR. And for the R, it's gonna be either 0, because if it was 0, what will happen is the next state will be resetted to 0. And if it was 1, the next state will be resetted to 0. So 0 and 1, what does it mean? Don't care. Okay, and the same. So here, look at this. My present state was equal to 0. The next state is equal to 1. What does that mean? that means the set was activated. Okay, so that's why I'm gonna put 1 here and 0 here. Now it was 1, the present state was equal to 1, and it becomes 0 at the next state. So what will be the value of the input required to get that next state? So for sure, the set should be equal to 0 and the reset should be equal to 1. And it was 1 and it stays at 1. So when it comes to the reset, for sure it has to be equal to 0. Now, for it, if the set was equal to 0 and the present state is equal to 1, the next state will continue to be 1. And if the set was equal to 1 and the next state is equal to 1, the circuit will set itself to 1, but still we have 1. So that's why I put here a don't care. So apply this to the JK flip-flop, you will get the same, except the fact that here, look at this. Here, if it was 0 and 1, no, it's not just, we have to make sure that J is equal to 1 and K is equal to what? To don't care. Because if J was equal to 1, I'm going to set my present state, which is equal to 0, to become 1. And if K becomes 1, this is 1, 1 represent a toggle state. So what does that mean? I'm going to toggle this 0 to become 1. Okay? So this is how we can interpret these table, and you can memorize it. It's up to you. Okay? So any question? Perfect, Rasha. Thank you. Okay, so in addition to the SR flip-flop and the JK flip-flop, and remember, those are flip-flop because we have the clock here, okay? If we don't have the clock, it's gonna be latches, okay? So in addition to these types, we have the D, which is the basic one, okay? And we have the toggle. And basically, these two slides is what you're gonna do at your lab 5, okay? The whole lab will be done if you just, understood, if you just understand these two slides. So at the D flip-flop, what will happen is the D is the basic building block for any registers, okay? If you want to save any bit, okay, you need to use the D flip-flop, okay? And at the D flip-flop, you have the D will represent the data input, okay? And so if regardless of what is the value of the present state, if D is equal to 0, the next state will equal to 0. If D is equal to 1, the next state is equal to 1, as long as we have a positive trigger from the clock. Okay? So look at this. So how I'm gonna derive the characteristic equation here? I don't need to do any kernel map. It's gonna be so easy, What I have to do is I just look Q next is equal to what? To D all the time, okay? That's it, 0 and 1, 0 and 1. So Q next will equal to D. So look at this here. This is the state diagram. The state diagram describes the function, the characteristic of your flip-flop in a graph way, okay? So what will happen here? Look, I have the present state is equal to 0. If D is equal to 0, I'm going to stay at 0. If D will become 1, I'm going to go to 1. And if D is equal to 0, I'm going to go back to 0. If D is equal to 1, I'm going to stay at 1. Okay? And can we get the value of D knowing what is our next state and the current state? 0, 0 means 0. 0 and 1 means D should be equal to 1. Okay, you know what? Okay, let's do it, like in the stupid way. The stupid way, Q next, copy Q next, okay? So this is 0, 1, 0, 1. I'm going to copy 0, 1 and 0, 1 because D is equal to Q next all the time. Okay? Now, the T flip-flop is something similar to the D, but instead of having, the value is equal to the input, what sometimes you want to do like some subtraction. So if I use a T flip-flop, I'm gonna get what? The inverter. Okay? The inverter of my T input, of my D input. Okay, so that's why the T flip-flop, if the T is activated, the next state will be the toggle value of the present state. If the T is not activated, the T flip-flop is basically a D flip-flop. Because look at this, the next state is equal to the present state. Okay, so let's what? Yeah, so let's take a look at this characteristic, like the state diagram. So if we take a look at this state diagram, can you hear me? Can you hear me good? Yeah, because I bought a new mic. Okay, so what will happen if I have, like, if I'm at state 0 and I have T is equal to 0, that means the next state will equal to the present state. Okay, I'm gonna stay at 0. If I am at state 0 and T is equal to 1, what does that mean? That means the present state will be toggled at the next clock, and it will transit from 0 to 1. That's why I'm gonna be at 1. Now here, if T is equal to 0, okay, if T is equal to 0, what will happen is I'm going to stay at my present state, which is equal to 1. And if T is equal to 1, I'm going to toggle this present state to become 0 at the next state. Okay, so if, look at this, similar to the D flip-flop, if we know the present state and the next state, can we get the value of the T? Now what you should do is what? The value of the T, look at this, will be an X NOR, XOR, sorry, X, it's an XOR between Q and Q next. Because look at this, if they are equal to each other, what I'm gonna get, what? Here's like, if they are unequal to each other, I'm gonna get 1 in the case of inequality. Okay, and in the case of the equality, I'm getting 0. What does that mean? That is an XOR. That's why for the Q next is basically, and even if we look at the truth table, so at the truth table we look here and we want to describe Q next. That's how we derive it. Q next. How I'm gonna write Q next in terms of T and the Q? That's basically is a XOR between T and the Q. Okay. So how I'm gonna, and this is will be at the final. Okay, that's like I'm gonna help you. How I'm gonna implement a T flip flop using a D flip flop. Can anybody tell me how? It's at my recording. Come on. Come on, guys. I want to implement a T flip flop using D flip flop. Yeah, but this will not cover. Okay, Lilia, you're somewhat right, but this will not cover when the T is equal to what? This will give you an inverted version of D all the time. But if D was equal to 0, remember the Q next should equal to the Q. Valentina, X or Q with C. No. Well, okay, let's do it the hardest way. Where's that whiteboard? Uh, I want a new bot. Bot. Add a new share. Okay, can you see this? So basically we have here, okay, yeah, but just 1 second. So I'll do it properly. Okay. Where's that tablet thing? Working area. Display to apply. Okay. So I have here a D flip-flop. Okay. That is a D flip-flop. It has D and it has the clock. The clock. And it has a Q and it has Q prime. And I want to change this D flip-flop to work as a T flip-flop. So what should I do? I will take a loop back from Q, go back here, and I'm gonna XOR it with what? With the T. And this is what I'm gonna input the D flip-flop. And here should be a clock. That is how I'm gonna implement a T flip-flop using D flip-flop. Now let's suppose that I would like to implement a T flip-flop using a JK flip-flop. So I have a Q and I have a Q prime. So what will be the answer? How I'm gonna make sure that this JK flip-flop will work as a T flip-flop at all given time? This is the new way of formulating this question. So let's remember the truth, like the characteristic equation, characteristic table of the JK flip-flop. So I have J and I have K and I have Q. So this is 0, 1, 0, 1, 0, 1, 1, 2, 3, okay. And 0, 1. So that is 0, 0, 1, 1, 0, 0, 1, 1. This is 0, 0, 0, 0, and 1, 1, 1, 1. Okay, now what will be Q next? Okay, I have nothing. So if like that is a case of what? No change, 0. That is a case of no change, 1. That is a case of a reset, 0. That is a case of a reset, 0. That's a case of set, 1. That's a case of set, 1. That's a case of a toggle. So that was equal to 0, it will become, it will become 1. That was equal to 1, it will become 0. So this is the trick. So if J and K was equal to 1, the JK flip-flop will work as a T flip-flop. So how I'm gonna do that? VCC. Okay? Yeah, maybe some of you got, okay, listen, if your input is D, just do D here. Remember, at the D flip-flop, we need an input. Okay? A data input. Okay? So this is working based on the fact that you have A XOR B XOR B. Boom. I'm gonna get A. So basically, the Q next is equal to D. So you are doing what? Like D XORed with D XORed with Q next. So this will give you what? D. If we are looking at from a reverse angle, okay? Now let's go back to the lecture. Okay, so that is, basically a quick overview about your, like whatever we covered in the previous lecture. Okay, but you need to go and watch it. Okay, so if I would like to analyze my synchronous sequential circuit, okay, so how can I analyze it? So I have to go and group whatever I learned from the previous two slides, okay, and then apply it in a modular level. So I'm gonna go look at the input, look at the output, as well as based on the characteristic equation of each flip-flop, I'm gonna determine what will be the states of that flip-flop. So let's take a look on an example. What the hell? Okay, 1 second. Yeah, by the way, I have uploaded those slides for you, okay? So, okay, can you see it now? I have the connection here. You see it? Yeah, whenever like Jason, you wrote it T input to both J and K. Yes, this will give you like if you're gonna use the T as the input. Yes, that's right. I did it to a VCC just to show them that it's one and one all the time. Okay, but you're right. So what will happen here? Where is mine? Okay, that's it. Yeah. What will happen is here, in order for this to be working as, if you have a T input, yes, use it to a T. So if T was equal to 0, that means the next state will equal to the present state. If T was equal to 1, this will become 1, and this will become 1, and this will be like a toggle. Perfect. Thank you, Jason. Okay? Okay. So now let's take a look on this this sequential circuit. So what I have, okay, let's pay attention to how I'm gonna analyze my following sequential circuit, and don't get scared. Like it's still there's boxes here. That's it. Don't worry about it. So we have two flip-flop. Okay, what does that mean? That means I have two, 2-bit per my circuit. So 2-bit means I am gonna get up to 4 states, because 2 to the power 2, I'm gonna get 4. Okay. So how I'm gonna determine what is the input of D0? Let's determine the input of D0 first. So the input of D0 is basically, I have an input X, okay, and I have a loop back from where? Loop back from Q1. So D0 will equal to X and it with Q1, okay, and the next state of Q0 will be equal to D0, because remember, it's a D flip-flop, and the D flip-flop, the next state is equal to the D input at all time. Okay, that's why I put here, look at the flip-flop equation. D0 and D1 is equal to X, and D0 is equal to X Q1, and D1 is equal to X Q0, because look, that is for D1, it's Q0 ANDed with X. Now the time here represents that this is like a sequential, a synchronous sequential circuit, and the time should be taken into consideration that based on the clock, we're gonna capture what the capture the values of everything here. So if you remember, like at lab 3, at grid 4, I ask you to do an operation. At grid 5, I ask you to do another operation. So the value of the input in relation to the time might change. Okay. Now to the state. Now what is the state equation? The state equation is basically the characteristic equation of the D flip-flop. So the next state and can be referred to as either plus or +1. Okay. So if you are at time 0, the next state will be time 1. The next state will become time 2. Okay. So it will be equal to D0, and I already know what is D0. Am I right? So that's it. Now the value, this circuit has an output. Okay. Okay. So in addition to the next state, we have an output, and that output is called Y. And this output is basically an AND gate between Q0 and the Q1. Okay. As well as the input X. Okay. So in general, we can refer to the next state as a sigma function. Oh, look at this, as a sigma function. That is sigma function of t that will represent my next state values. Okay, I don't want to mix it with output. Okay, of my flip-flop. Okay, the sigma, and the lambda of t will represent the value of the output. So we have an output here. Okay, so as we're gonna discover here, if the lambda and sigma are equal to each other, that's called a Moore machine. And if they're not equal to each other, that's called a what? A Milli machine. Okay. So now, okay, let's forget about these fancy Roman letters. Okay, and let's follow the tedious approach, which is basically I'm gonna I know what's my input, what's my output, and that's it. Okay, so nothing else. Now since we have, look, how many like flip-flop we have? We have 2 flip-flops. So each one of them can give me either 0 or 1 at the next state. Okay, so I'm gonna have a table, this state table. Okay guys, will have 4 values because each one will give me 1 bit. So both of them 2 bit, 2 to power 2, 4 values. Okay, so if I am at state 0, 0, okay, what will be the next state? Is it a rocket science to find it? I want an answer. I would love today, I'm high. I want interaction with me. What will be the next state? So the next state is not a rocket science. Remember the equation we derived it here? We're gonna use it in order to get the next state. So for Q0, okay, for Q0, what is the output? The output is equal to X Q1. So what is X Q1? Okay. Yeah. I remember, like, this is should equal to what? Okay, let me rewrite it in a way that you're gonna understand it better. Okay. So I have here Q1, Q0, and X. Okay. 0, 1, 0, 1, 0, 1, and 0, 1. This is 0, 0, 1, and 1. Okay. 0, 0, 0, 1, and 1. That is 0, 0, 0, 0, and this is 1, 1, 1, 1. Okay. And the output here is we have a Q here. Okay. Q next, 1, Q0 next, and Y. Okay. So, oh, okay. So remember, we have here 0. We got 0 here, and we got 0 here. Then we got 0 here. Then we got 0 here. And for this one, still 0. For this one is going to be 1. And for this one, it's going to be 0. For this one, it's going to be 1. Okay. And what will happen here? Here is going to be what? Like I'm going to add these. So 0, 0, 0. Now here, 1. Here, 0. Here, 0. Here, 0. And here, 1. Thank God. Okay. And for Y, what is the value of Y? Y is the AND of all of them. Okay, so basically I know what's Y. It's going to be 0 all the time, except this one. Okay. So that is the how you're gonna analyze your how you're gonna analyze your circuit. So if you are, let's do it this way. How many states we have? We have 4 states. So we have here 0, 0, and let's go here and 0, 1, and here we have 1, 0, and we have here 1, 1. So if I am at state 0, 0, which is these 2 rows, okay, and the input changed, okay, and the input change from 0 to 1, what will happen? I don't care. I'm going to stay here. Okay. If I am at state 0, 1, okay, here, and the input is equal to 0, I'm going to go back to 0. Okay. So if I am here and my input is equal to 0, boom, X is equal to 0, I'm going to go back to 0, 0. If I am at 0, 1, and the input is equal to 1, what will happen? I'm going to go to state 1, 0. X is equal to 1. Okay. If I am at 1, 0, and the input is equal to 0, I'm going to go back. Here, look at this, guys. Here, look at this. I am here now. I'm tackling these two. These two. I am at state 1, 0, okay? And the input was equal to 0. What is the next state? It's going to be 0, 0. So that's why, come on. Oh, no. Come on. That's X equal to what? X equal to 0. Because I'm going from 2 back to 0. Now I'm at state 1, 0, and the input is equal to 1. Where I'm going to go? Oh, I'm going to go back to 1. So that's why X is equal to 1. Okay. Now I am at state 3, which is 1, 1. The input is equal to 0. What will happen? I'm going to go to 0, 0. X is equal to 0. Now, if the input is equal to 1, I'm going to stay at myself because that is this case, okay? Here, this is this case. So this to encode the state, the present state, and this to encode the next state. And this is the input. The input is equal to 1. Go back to yourself. X is equal to 1. Okay. So that is exactly what I did here, but I did it in a way easier for you. Okay. Now for the output, yes, sometimes what we have to do, okay, guys, sometimes, where is yeah, for the, sometimes you're gonna see this, this format. So X dash Y. So that is 0 and it's gonna be still 0. The only case it's gonna be 1 1, it's here. It's gonna be just 1 and 1. So the one here to indicate X and the one here to indicate Y. Everywhere is gonna be just the X who will determine the next state, and the output of the Y is gonna be 0 all the time. So this here to encode it is gonna be 0 and 0. This here to it's gonna be 1 and 0, and this one is gonna be 1 and 0. Okay, so that's it for the state. We can have another example, so don't worry about that. Okay, okay, guys. Now let's take a look on this example. Okay, this is another example, and I'm using this like, you know, that's exactly. So I have two D flip flop here, and those D flip flop are connected using a combinational logic, okay, with the loop back. That's why it's a sequential, and we have a clock. Okay, so what is our goal? Again, our goal to analyze it by getting what is the value of the input, and the value of the input is equal to the value of the next state, because that is what, that is like that's a D flip flop. Okay, so so that is my goal, to find what is the next state, because I have, this is like a flip flop A and a flip flop B according to whatever, like, you know, labeled here. Okay, so that is, you know, sigma A sigma B as a function of the current input and the current state. Okay, and for the output, which is, you know, which will equal to, you know, like the lambda of the current input and the current state. Okay, so those fancy letters means nothing to me. Okay, nothing. Nothing to me. Why? Because what I'm gonna do is I'm gonna go look at the input D here of DA. What is the out, what is this input is depending on what? Oh my God, look at this. This is depending on a loop back here, and this loop back is taking it with A, and a loop back from B here. They AND it together, and both of them, they're OR together. And since the input of a D flip flop is equal to the like, you know, is equal to the next state according to the characteristic equation of a D flip flop. So DA will equal to what? To the next state of A. And we'll do the same thing for B. Look at B. B is a poor guy. I like B. So B is basically an AND between the, you know, look at this. It's an X as well as A prime. Okay, that's it. So I was capable to find what is the input of B, and since the input of B is will equal to the next state of B, that's why I put B plus. Now I know these equations. Okay, so I'm gonna write my state table, and this table, this state table, I have, you know, I have, like, you know, two flip flop. So they will give me like 2 bits, and I have an input. Okay, so what will happen is I'm gonna have 4 states, but 8 possibilities with the input. Okay, because like I have 3 variables now. Okay, so what will happen here? Okay, for let's determine the next state of A. I have 0 0 and 0 applied to this equation. Okay, 0 and okay, this will give you 0 all the time at this cell. Okay, and we have to go vertically. Okay, forget about B plus. Now we are tackling what is A plus. What is your grade at this course, or what is your, the next state of the first flip-flop. Now I have 0, 0, and 1. Oh, good. I'm gonna still have 0. Then I have 0, 1, and 0. Okay, 0 ended uh, with 0. This will give you 0. 1 ended with 0. This will give you still 0. Now at this case, I have this term will give me 1. So regardless of this one, I'm gonna get 1. That's why I put 1 here. Okay, and so on. Okay, that's what we're gonna do for A plus. Now for B plus, okay, what we'll do is we apply this equation. So it's something like you're doing a truth table. Okay, so we're gonna add x with the complement of A. So that's basically 0 ANDed with 1 is still 0. 1 ANDed with 1, because we're gonna complement A at the current state, it's gonna give you 1. Okay, now let's go here. 0 ANDed with 1 is gonna give you 0. 1 ANDed with 1 is gonna give you 1. Okay, and so on. Now look at this. What will happen is we're gonna go and we have the output, and the output is basically whatever. What's the output? Look at this. We're gonna just follow the output. The output is equal to, I'm complementing x here, and I'm ANDing it with what? With A, and then I am, I am taking a junction here. So I'm taking x. So it's x prime plus x prime. It's like this, like this. X prime A plus B. Okay, and that's how I am gonna find the value of y, not based on the value of the next state. No, this has to be calculated based on the value of the present state as well as the present input. Okay, so this will gonna be my y value if I am apply this. So let's take two cases. So this will give you 0. You AND it with 0. This will still 0. And let's take a look at this case. Okay, this case. Okay, this case. Why I'm getting 1. So that is exactly that. It will be 1 plus 1, and it with the complement of this, which is 1. That's I'm gonna get 1. Okay. Now look at this, guys. These two rows will indicate as 0. These two rows will indicate as 1. These two rows will indicate as 2. These two rows, sorry, will indicate as 2. And these two rows will indicate, come on, as 3. Okay? So this is 0, as 2, and as 1, and as 0, as 3. So what we're gonna do? Okay, if the input was equal to 0, the next state is equal to 0. That's why I'm staying at my next state. And what was the output? Still 0. That's why I put 0, 0. Okay. Now, if the input is equal to 1, the next state is equal to 1. Here, that's my case. And the output is equal to 0. So that's why when it comes to 1, that's what I'm gonna do. I'm gonna go here, and this will give me what? This will give me 0, 1, the next state, and the output still equal to 0. Okay. Now, if I am at 0, 1, and the input is equal to 0, I'm going back to state 0, 0, 0 here. Okay. That's why, boom, I'm gonna go here. But at this case, the output is equal to 1. That's why I have 0 dash 1. Is that clear? And what will happen is now I'm at case what? 0, 1, and the input is equal to 1. What is my next state? Oh, 1, 1. So I'm gonna go to 3. So 0, 1, the input is equal to 1. I'm gonna go to 3. What is the output at that level? Please, the output at that level 0. That's why I'm gonna put 0 here. Okay. So that is the present state. Look at this. Okay, let's zoom in. This is the present state. That's the input dash the output, and that's the next state. Okay. Clear, guys? Is it clear? Okay, how are you? Good, you know that. Let me pick a name here. Name. Luca, is it clear? Okay. Where's the document that I already shared? I'm gonna share it again. Yeah. Okay. Okay. So what do I mean? Okay, any sequential circuit is referred to something called finite state machine. Okay, why finite state machine? Because we will definitely go to an we will change from one state to another state. Okay, so any sequential circuit can be described as or categorized as a milli model or a Moore model. So what is the difference between milli and Moore? The difference is so easy, it's so simple. If your output is depending on the the state only, it's gonna be a Moore machine. If it depends on the input and the state, it's gonna be like a milli machine. Okay, let me give you an example of that and look at this. Okay, man, I hate this Adobe Connect sync. Yeah. Okay, look at this, guys. So the mini machine, your function one, depending on both the input and the present state. Okay, and that is an example of a mini machine. Look at this. Y has will be for sure like a function of the present state of the first D flip flop, the second D flip flop, as well as the input X. That is a mini machine. At the Moore machine, what will happen is the output will depend only at the present state. Look at this example. Okay, so the output here is basically an AND between the next state of the first flip flop and the second flip flop. Do we have any connection with it with the input? No. You see, if Y just depends on the next state and has nothing to do whatsoever with X, that's called the Moore machine. Now the present state still depend, the next state still depend on the input, but the output Y does not. Okay, so that's an example of a Moore machine. Okay, now let me move to another topic, and then this is an interesting topic. Okay, guys, so now let's suppose that I have this state diagram, and look, this state diagram will make me crazy. Okay, so I have one input and one output. So that circuit, it has one output and one input. Okay, and how many states I have? 1, 2, 3, 4, 5, 6, 7 states. Oh my God! So I need 3 flip flop to encode them. Okay, so can I minimize them? So how to do so? What you need to do is first of all to write your state table. Okay, so let's take a look at state table here. So if I am at state A and my input was equal to 0, okay, what will be my next state? Still A. If my input is equal to 1, what is my next state? I am at A. my input is equal to 1, my next state will be equal to what? To B. That's why I put B. And remember, the output of, like, that is boom. Okay, that is what? That is a milli machine, because look, the output might change based on the value of the input. You see that? Okay. So if I am at if I am at input 0, okay, what is the value of the output? The output should equal to what? Should equal to 0. If I am at like state A, and I'm like the input is equal to 1, the output is still 0. So that's why I'm gonna put 0. So after listing this state table, I'm gonna take a look at E and G. Look at E and G. The next state is A, F, and the next state here at A, F. My God. And the output is still the same, is 0, 1, and 0, 1. Okay? So, AF, AF. So what should I do? Why should I complicate myself by having two different states, as long as E and G can be replaced by one state? Therefore, I'm going to delete G. I don't care about G, because for sure I don't need it. Because at E, if the input is equal to 0, I'm going to go to A. What is E? Let's take a look at E. The input is equal to 0, I'm going to go to E, and the output will be 0. And if the input is equal to 1, I'm going to go to F, and the output is equal to 1. And that's exactly what's going on with G. If the input is equal to 0, I'm going to go back to A. And if the input is equal to 1, I'm going to go to F. So basically, there is, similar to the map, guys, like you have multiple, at Google Map, you have multiple paths, and the same will, these two paths will give you the same cost. So what we'll have to do, just try to remove one of them. So I decided to remove G. So that is your minimized state table. Okay. And imagine that we could have minimized another state. So instead of having 3 flip-flop to encode this state table, we need just 2. Okay. But that doesn't apply to this case, because here we have 1, 2, 3, 4, 5, 6. So 6 means I have to have at least 3 bits. So 3 bits means 3 flip-flop. Okay. Okay. Now we have learned how to what, guys? We have learned how to analyze the circuit. But what about that? I want you to design a sequential circuit. So what should you do? So the answer for this question is so easy. Look at these steps, just follow them. Okay. So based on the problem statement that I'm gonna give you, you have to rewrite it in a way that will, that you're gonna break that statement into sub-statement, and try to symbolize each subtask or sub-statement into a state. Okay. And try to find a relationship between those states. Okay. And once you did that, you can develop the state table. And by looking at the state table, if 2 states are sharing the same output and the next state, we can omit one of them. Okay. Then after that, you assign a binary value. So instead of writing here, instead of writing, I have as 1. Okay. And let's suppose that I only have like 4 states. I'm gonna refer to this S1 as 0, 1. Okay. And for S3, state 3, I'm gonna refer to it as what? 1 and 1. Okay. Now, and if I did not ask you to choose the type of flip-flop, okay, choose the D flip-flop, because it's the easiest. Okay. Now, if you're gonna do it like using a JK flip-flop, please pay attention that Now let's suppose that this is what? This is a T flip-flop. Okay, this example here, that is a T. That is a T. Okay, so you're gonna say that T is equal to, what is t is equal here? Let's take a look at here. T is equal to, okay, forget about this, okay, is x ANDed with q1. And that's for t what? T0. And for t1, that is x ANDed with q0. Now, the next state will not equal to what, guys? The next state of q0 and q1 plus will not equal to t, guys. Why? Because it's not a d flip-flop. What is the value now? The value of q0 plus will be equal to, remember, equal to the value of t0 that you have calculated, XORed with what, guys? With a q0. And the value of q1 plus will be equal to t1 that you already calculated here, XORed with q1. So your table, instead of having just q0, no, here, q1, q0, q1, no, sorry, t, no, x here, then you're going to have a value of t0 and t1. Then the next state, which is q1 plus and q0 plus. So whenever you want to calculate the values at each column, what you have to do is to XOR t0 with q0 for to find sorry, let's suppose that we're doing it for q0. So we are XORing t0 with the q0, and for q1 we're gonna XOR t1 with q1, and that's how you're gonna define this. Find this, okay? Okay, guys. So and after that, what, like, you know, after we choose, so we derive the simplified flip-flop and output equation, and we draw the logic diagram. So let me give you an example, okay? So the example that you want to design a circuit that detects a sequence of 3 or more consecutive one in a string of bits coming through an input line. Okay? So if you are at, so what does that mean? Okay, 3 or more consecutive ones. I don't have 3 or more consecutive ones. So that means, okay, guys, I need like 4 states. Okay, and those 4 states as S0. So what will happen is if the input is 0, I'm gonna go back to 0. And if the input is equal to 1, look at this. If the input is equal to 1, I'm gonna go to S1. That means, okay, that's the thing, is this is the state. Okay, so you have here, like, you know, the only time the output will equal to 1 when you are at S3, because 3 ones are detected, and that means that I'm gonna get 1 and 1. So after this, what will happen is, after you wrote this state diagram, what will happen? You translate it to a state table. Okay? So if I translate this as a state table, okay, and by looking to this state table, so at the state table, you have input X, okay, at which it was 0, and then it was 1, and you have Y. Now, by looking at this, if you are at 0, the next state, we're going to take a look at this state diagram. So 0, the input, like if the input is equal to 0, I'm going to stay at my state. That's why I put S0 here. And if the input is equal to 1, I'm going to go to S1, and so on. So after I look to this state table, I can find any state at which they're sharing the same state, the same next state, as well as the same output. Therefore, there is no equivalence, and as such, I'm gonna stick with having 4 states. Okay? No, there is no equivalence. So if you are at S0, you have S0 and S1. and here you have S0 and S2, S0 and S3, and S0 and S3. Now don't get fooled, because yes, these they share the same next state based on the value of the input, but the output they're different. Therefore, I cannot combine them. Okay. So after that, what I'm gonna do is I'm gonna encode these in a binary coded. Okay, so that is 0 0, that is 0 1, this is 1 0, and this is 1 1. And by having this table can be rewritten at, the biggest table here. Okay, so what will happen if I choose to do it with a D flip-flop, and this is the easiest way? What will happen? I'm gonna have two flip-flop, one for A and one for B. But what is the input for the A, or what is the input for the B? Now remember, the input of A and input of B will be equal to the next state. So can I minimize the next state in terms of the whatever I like, whatever the input I have? So what I can do is simply writing a true, like a Kernoff map, that is for A plus and that is for B plus, and I'm gonna fill the cells from here, from these three, like three variables and this 8 possibilities. So that is exactly what I'm gonna do. Okay, guys. Okay, so let's take a look at that table here. So the next state was equal to 1 at where? At 3, and was at 5 and at 7. Okay, so let's take a look here. So this is that is 7, that is 3, and that is 5. You see it? Okay, now the next state here was equal to what? Was equal to 1 here at 1, this row, and at this row, no, at this row at 5, and at 7. So 1, 5, and 7. Let's take a look here. So that is, remember, guys, remember that is 0, 1, and this is 0, 0, and this is 0, 1. So this is 0, 0, 1. So that's why I have 1 here. Okay. Now, if you look at this slide, you will see that the input, okay, so basically what I'm finding what is the value of input A and what is the value of input B for the D flip-flop, okay, which is basically the same column of A and of the next state of A, and the same column of the next state of B. Okay, guys. And when it comes to the Y will only be high, okay, in case of I have, you remember, like a sequence of 3 1s. So that is state 3 and state 3. So that's 1 and 1. So if you do the Kernoff map here, in terms of, look, guys, in terms of not the next state, in terms of A, B, and X. A is the present state. It's the one here. Present state here. And the input here. Okay. So after that, after I got the minimized equation, and I know I have two flip-flop. Okay. So I can, draw the circuit. So I have two D flip-flop. Okay. The value of D A is equal to AX plus BX. That's why it's going to be what? A with X, that is AX, and this is BX, and this is the OR between them, okay? That is for the first flip-flop. And for the second flip-flop, the value of DB is AX plus B prime X, okay? That's why I'm going to negate B, or I'm going to take the complement of B, okay? And this is B prime X, and this is AX. I'm taking just a line between this one, That's AX, and this is the or four of them, and this will be DB. Okay, and for the output Y will be what? The output Y will be an AND gate between what? A and B. So is this a Mealy machine or a Moore machine? So Y can be written as a function of A and B after we simplify A and B. Do we see anything for the X? No, that's why it's a Moore machine. Okay, guys? Okay, was it hard? Okay, not too bad. That means it was bad, but not too bad. Okay, you need to revise it, okay? Okay, so let me here share that documents again with you. And as long as I think it's good. Or, okay, let me share another one. Let me share another one. Where is the documents? Uh, Mod 5 to. Okay, so what we're gonna do now is you have, okay, so I shared it this way. So using a PDF, so you know, like because the Adobe doesn't do it properly when it comes to the PowerPoint, okay, it doesn't convert it properly. So now, if you have any question, you have the slides by yourself, and you can ask me. I'm all yours, okay? Now let me try to enable what your mic. Uh, okay, so guys, can you enable? Anybody would like to speak with me? So you can see at the left side, at the top left, there is a way that you have your mic. Can you enable it? And you need to raise your hand. You don't see your mic? Okay. So just raise your hand. I'm gonna move you. You can raise your hand. Okay, I can see it. Can anybody would like to talk to me? Raise your hand. Okay, where are you, Valentina?
Hello, can you hear me?
Yes.
Okay, I just had to plug in some headphones. It just didn't work with my computer mic. For the very first example that we saw,
Which one?
the one where the lines didn't show up in the slide, so you had that one.
Yeah.
Okay, so when you were doing the table for the output
Yeah.
in like the separate doc, you said that Q1 was equal to X and Q0, I think, like Q1, but I thought it was
No,
supposed to
no.
be an
Look at this, Valentina. Valentina, look, it's so easy. Y is equal to what? An AND gate between Q0, Q1, and X.
Mhm.
So y will be equal to 1 as long as all of these guys are equal to 1.
Okay.
That's why.
But then to figure out Q1, what did you use again? Like
I'm going to use the
of
current
Q1.
state. The current state. Q1, Q0, and X. The current state. Look at this. Here. The current state, okay? So 1, 1, and 1. So the current state will give me 1.
Okay.
Okay?
Okay, that makes sense. Thank you.
Welcome. Anybody else? No, why do you want to ask me in a private? Why do you would like to ask me in a private? It's a lecture day. It's not an office hour. Okay, stay to the end. Stay to the end, okay? Okay, who else? Howard, is it good? Good, buddy. Okay, so basically you don't have any question, huh? Okay, so let's wrap everything. So that is the end of
Sorry,
module. What?
me again. I have one question, real quick. Why would you want to pick like a T um flip flop instead of a D flip flop if it's just easier to work with a D?
Because you need to learn everything. Okay.
Okay.
Yeah, that's it. It's like it's just the fact that you need to learn. You need to learn how to do addition and how to do subtraction and how to do multiplication. You know. So do we need to learn how to do multiplication? No, because
Yeah, I know how to
multiplication
do
is
addition,
basically
but
an addition.
yeah.
But yeah, we need to learn these skills. Okay. At the
Okay.
end of the day, yeah. At the end of the day, it's up to you, okay? But if I ask you using T flip flop, you're gonna use a T flip flop. If I ask you using JK flip flop, I'm you're gonna you have to use JK flip flop. So at module 6, we're gonna go over registers and counters, and they're basically what an examples of a synchronous sequential circuit. And you're gonna see that how I'm gonna design it with the JK flip flop or with the T flip flop, okay? But just for the sake of simplicity for this, for this lecture, I've shown it with the D flip flop. Okay.
Okay. Perfect. Thank you.
All right. Yes. So if you have any, if you don't have any questions, and it's 1:04 now, I believe that the timing is gone. So all please quit the meeting, and we'll catch you like on next week. And just to wrap up everything, assignment 5 will cover both modules. Okay? Okay, where is that guy? If you would like to talk to me, just stay around. I'm gonna break the room into multiple rooms so we can talk in a private. Okay, because I need to stop the recording. I don't want that private talk to be going in the recording. Okay, so I'm gonna stop the recording.